Hello, everyone. Welcome to the lecture 1. Lecture 1 is the first law of thermodynamics. As we talked about before, we have to first define the system, and we define its surroundings. Then we discuss what exchanges can take place between the system and its surroundings. So it turned out there are 3 types of exchanges we can do. We can add or remove heat, work, or mass of component between the system and its surroundings, represented by dq, dw, and dni for the component I. So notice we have here is that if the added new system is positive, if the removed of system is negative. So we want to find a quantity for the energy of a component. Is Ui, is the energy of a component I, Ui. So total energy added to the system will be dq plus dw plus summation of Ui dni. So Ui here is per ni. So it's a new unit energy. The first law of thermodynamics is about the energy conservation. That means the energy change in the system and its surroundings are together should be conserved. So it will be 0. We discussed that total energy added to a system is dq plus dw plus summation of ui dni. So the change of internal energy of the system must equal to the energy added from its surroundings, which is dq, dw, and ui dni are together. So those additions of energy into the system must increase the internal energy of the system. And this U sometimes also called the total energy, E. So U and E are exchangeable in our thermodynamics here. It's very important to realize that the first law does not concern the state of the system, whether it's stable, metastable, unstable. Whatever energy you add into the system will increase the internal energy of the system. It's independent of the state of the system. So now we talk about the exchanges of heat, work, and mass between the system and its surroundings. So we have some conditions for this change. We can make constraints. So if we allowed all of them change, so we call it open system. So dq, dw, and dni, they can all exchange between the system and its surroundings. However, if we say, no, you cannot do heat exchange, then that's called adiabatic system. dq equals 0, but you can still exchange work and mass. If you constrain the system, say, oh, no, you cannot change mass, but you can still change heat and work, that's called a closed system. But if you do not allow any exchange, dq and dw, dni all equal to 0, we call it isolated system. So you can see we have 4 types of systems we study. Everything can be exchanged, and one cannot be exchanged, or all cannot be changed. There's no name for a system called dw equal to 0. That's interesting. Maybe we should find a name for that. Maybe there is one I did not know. Okay, let's talk about heat. Heat is thermal energy. For example, it's from the sun to the earth. And its unit is joule. Units is joule, J symbol. And the heat can be transferred in three typical ways. Conduction, you have direct contact, convection through fluid flow, or radiation, electromagnetic waves. So the heat from sun to earth is transferred through radiation. Work. I show a picture here, photo here, that a blacksmith is hammering a piece of metal. So that work is the blacksmith does the work to this piece of metal. So it's a force acting over a distance. So here is mechanical work. Mechanical work can be hydrostatic, that means all directions the same, and non-hydrostatic. Different directions are different. Could have electrical work, so it's electric current pushed by the voltage. Or magnetic work is the magnetization by the magnetic field. So there are mainly three types of works can be done: mechanical, electrical, and magnetic. So the last one I have to talk about the components and the internal energy. Okay. So we have to be clear that when that summation is independent components. That means it can be controlled independently from the surroundings. I just added animation for this slide, so it won't distract you too much. So here we talk about the component and the internal energy. Okay. So we have to realize that the components we talk about here are independent components. That means they can be controlled independently from the surroundings or from the system. And with dq equals 0 adiabatic, and dw equals 0, no work exchange. If you consider only change of one component, okay, then we can find that ui is equal to the derivative of the total energy to ni derivative, partial derivative. So you can see that the ui is actually the partial total energy of a component I for a partially open system, because it only changes the ni here, right? So we also know that from the relativity, the total energy of a system, E equal to mc squared. Okay, so but this energy of is huge. It's not what we study in thermodynamics. It's more like a nuclear physics or relativity this way. So where in this equation, m is the mass, c is the speed of light. Lecture 2.